In 2022, astronomers utilizing the Murchison Wide Field Array discovered an unusual new radio signal that was arriving consistently every 22 minutes. These astronomers were not unaccustomed to the detection of such recurring signals. They are typically generated by pulsars, which are dense neutron stars that emit intense, directional beams of light across the cosmos as they rotate. However, as the team initiated a deeper examination of earlier observational records, they realized this peculiar signal had been reaching Earth since at least 1988 with extraordinary stability. A stability far exceeding expectations for a pulsar revolving every 22 minutes. If this source was a neutron star, it was unlike any previously observed. Thus, the pressing question began, and you're watching Astrum. Join me today as we grapple with the core mystery behind this signal, an enigma that threatens to fundamentally challenge our current comprehension of some of the most awe-inspiring celestial bodies in our universe. The location of this source, officially designated as GPMJ 1839-10, is approximately 18,000 light-years away. Its transmission is received as pulses, which can endure for any time duration between 30 seconds and 5 minutes. These individual pulses may appear at any point within a time window of slightly over 6.5 minutes, centered precisely 22 minutes after the preceding pulse. To us, this might suggest a considerable degree of variability. 30 seconds and 5 minutes represent vastly different lengths of time, and the pulse arrival window fluctuating by over 6 minutes doesn't immediately suggest an exceptionally stable source. Nevertheless, the dynamics of neutron stars can be incredibly complex. If the source is indeed a neutron star, numerous contributing factors could influence the duration and arrival times of the pulses we detect. Despite these complexities, the astronomers successfully identified this signal, hidden within data spanning the last 35 years. They leveraged this expanded dataset to mathematically average out the observed fluctuations. They calculated that the source completes one rotation every 21 minutes and 58 seconds, and they also determined the amount by which it had decelerated. Yet, to their astonishment, their calculations showed that this rotational period had remained essentially unchanged over the past 35 years. Even though such an object is expected to slow down as it radiates energy into space, we can only state with certainty that if the source has slowed down at all, its rotation period could not have increased by more than 0.28 milliseconds over that 35-year observation period. Detecting any greater increase would have been possible with the available data. This is an absolutely minuscule amount, demonstrating that whatever the nature of this object, it is spinning with truly remarkable stability. This high degree of stability is generally not unusual for a typical pulsar. They are often regarded as the timekeepers or clocks of the cosmos, mechanically ticking away with such precision that we can use them to measure time across immense distances in space. However, this level of stability is highly unusual for a pulsar that is spinning so slowly. To grasp why this combination is so perplexing, we must briefly review how pulsars operate and the mechanism by which they gradually lose rotation speed over time. Pulsars are neutron stars, the compressed remnants, the leftover cores, of massive, deceased supergiant stars. Excluding black holes, they are the densest objects known in the universe. Planets, like our own Earth, are fundamentally composed of atoms which consist of over 99.999% empty space due to the enormous distance separating the electrons from the incredibly dense nucleus they orbit. But now, try to imagine an entire star formed purely from the neutrons found in that nucleus. No electrons, no protons, no empty space. Just a single teaspoon of this material would possess a mass equivalent to 11 times that of the entire human population, currently around 8 billion people. A typical neutron star is about 35% more massive than our Sun, yet it is squeezed into a sphere with a diameter roughly the length of the island of Manhattan. To merely call it dense would be a colossal understatement. For reasons that remain a mystery to astrophysicists, this extreme environment generates an unbelievably powerful magnetic field. How does this relate to the radio transmissions we intercept from pulsars? And where exactly do the light waves originate? To properly address this, we need to understand a complicated process that produces the signal. An exponentially growing shower of light and matter, all commencing from a solitary electron. Close to the magnetic poles of a neutron star, an electron can be accelerated by the intense magnetic field, causing it to emit a curvature photon tangential to the magnetic field line. This marks, if you will, the commencement of a pulse. The curvature photon travels in a straight line until the angle between its momentum and the magnetic field line becomes too large. Once this angle reaches a critical threshold, the light dissipates, transferring its energy into the quantum field of electrons. This energy manifests as the creation of an electron alongside its antimatter counterpart, the positron. The newly formed electron-positron pair possesses a certain momentum perpendicular to the magnetic field lines, which they spontaneously shed in the form of synchrotron photons. Each of these two synchrotron photons can then, in turn, generate another electron-positron pair after they themselves reach the threshold angle between their momentum and the magnetic field lines. This complex process repeats again and again, leading to an exponential increase in the quantity of photons and electron-positron pairs created, until the synchrotron photons no longer carry sufficient energy to produce additional electron-positron pairs, thus concluding the cascade. These resulting photons are then beamed out into space, while the initial electron continues its trajectory, generating more curvature photons and subsequent cascades as it moves along the magnetic field lines. This pair production cascade is the reason a pulsar's light is so exceptionally intense that we can detect a signal from this tiny stellar remnant, despite it being thousands of light years away. But why do we perceive this light as distinct pulses rather than an uninterruptedly glowing beacon shining towards us? This is because the magnetic poles of a neutron star are seldom aligned with its axis of rotation. Just as on Earth, the magnetic North Pole that guides our compasses is not identical to the actual geographic North Pole the Earth rotates around. Therefore, pulsars function like colossal lighthouses, sweeping their beams of light across the cosmos as they spin. For a distant observer, like us on planet Earth, we witness these beams pass by us repeatedly as the pulsar completes its rotation on its axis. These detectable bursts are the pulses of light that our telescopes record. Notably, this is light with extremely long wavelengths, lying in the radio part of the electromagnetic spectrum, meaning only a radio telescope can detect it. The light produced by the cascade maintains the same wavelength, with the peaks and troughs of the light waves fluctuating in unison. The light waves are also polarized, meaning they are all aligned along a single axis. This is a signature characteristic of neutron stars, and this is precisely what the 22-minute signal exhibits. The signal also includes rapid fluctuations that persist for between 0.2 to 4 seconds, during which the light's polarization axis abruptly shifts by 90 degrees, perpendicular to the original axis, and then returns. This effect is yet another key signature of the particle cascades occurring at the pulsar's poles. So much of the observational data points strongly toward a pulsar being the source of the signal that one might assume this is an open and shut case. However, one crucial variable, which we noted earlier, casts the entire theory into doubt. The slow rotation rate of the neutron star, or more accurately, the combination of its slow rotation rate and the extraordinary stability of that rate. You see, as pulsars shed energy by emitting their powerful beams into the cosmos, the principle of conservation of energy dictates that the pulsar must slow down. Eventually, the pulsar decelerates so much that it can no longer generate the power for the pair production cascades, and the light emission process effectively shuts off. At this point, the pulsar is considered to have entered the so-called death valley. A graph plotting neutron stars based on their rotation period on the x-axis and the rate of change of that period on the y-axis illustrates this. The death valley is represented by a gray band running through the middle. Any pulsar exhibiting properties below this boundary should, theoretically, not be shining as the bright cosmic lighthouses they typically are. We observe that our signal falls even below the absolute lowest line marking the death valley. This implies that if it were a pulsar, it should be definitively and completely switched off. Yet, we are actively detecting it. Consider the cluster of other known neutron stars on this graph. They usually spin between 10 times a second to once every second. In comparison, our mysterious signal has a rotational speed of once every 1,318 seconds, which is over 1,000 times slower than the typical pulsar. This slow rate would be acceptable if it were also slowing down rapidly, which would move its data point upwards on the graph, placing it above the death valley. Such a rapid rate of energy loss would sufficiently power the pair production cascade required to illuminate the neutron star beacon. However, this neutron star is mind-bogglingly stable, making its detection seemingly inexplicable. The astronomers who discovered this signal considered an alternative mechanism that might account for how a neutron star with these properties could still be producing light. Perhaps the neutron star is a magnetar. A magnetar is a type of neutron star characterized by an unusually powerful magnetic field, perhaps more than 10,000 times the strength of the weakest neutron star magnetic fields. Magnetars are known to undergo starquakes, cataclysmic events that release the tremendous tension stored in the neutron star's outer crust. These stresses are created both by the magnetar's powerful magnetic fields and by the deceleration of its rotation. A rapidly spinning magnetar will develop a bulge at its equator due to centrifugal force, distorting it from a perfect sphere. As the magnetar slows, the outer layers must adjust to a new equilibrium and reduce this bulge. The crust violently snaps into a new configuration, temporarily realigning the magnetic fields and powering a massive release of energy as light that we can detect on Earth. The most powerful starquake ever detected, that of SG 1806-20 in 2004, released such a colossal amount of energy that if it had occurred just 10 light-years from Earth, it would have caused a mass extinction event. If anything is capable of lighting the beacon of a dead pulsar, this phenomenon would be it. So, could GPMJ 1839-10 be a magnetar that has recently experienced a starquake? Have we resolved the mystery of the 22-minute signal? It appears not. We expect these starquakes to also emit light in the X-ray part of the spectrum. Yet no X-rays can be detected from the source's position, roughly 18,000 light-years away. Furthermore, it would be inconsistent for a magnetar outburst to persist for 3 decades. A starquake is a temporary event, and the released energy typically dissipates within a few years at most. It is simply incomprehensible that this signal could have endured for 35 years if its cause were a magnetar. Once again, the unique properties of our signal rule out its identity as a standard neutron star, or even an unusually powerful one that has undergone a special event like a starquake. But what other object could possibly be the source of this mysterious signal? The astronomers who discovered it proposed a few other possibilities for the source's identity. One possibility is a highly magnetic white dwarf. A white dwarf is another type of stellar remnant left behind after the recent death of a star, but one that lacked the necessary mass to collapse the empty space within its atoms and transform into a neutron star. A remnant with an exceptionally strong magnetic field could potentially produce radio emissions, and since it is not a neutron star, it could get away with being as slow and stably rotating as the source of our object while doing so. The key issue is that this would require an exceptionally strong magnetic field, far greater than any we have ever observed on a white dwarf. AR Scorpii is the only known radio pulsar that is actually a white dwarf, and its radio emissions are 1,000 times less luminous than the source of our 22-minute signal. So, if a white dwarf is unlikely, what are the remaining options? Astronomers have observed low-frequency radio waves originating from the interactions between stars and exoplanets, as well as from a binary system of two brown dwarfs revolving around each other. But this type of emission is typically much weaker, approximately 100 million times weaker than the source of our signal. In conclusion, it seems that none of our established theories can fully explain the 22-minute signal. While the unresolved question about the source of the signal might feel frustrating, this is precisely the kind of mystery that astrophysicists seek. When scientists encounter new data that challenges long-held theories, it often ushers in revolutions in our understanding of the universe around us. Here, our already tentative understanding of neutron stars is being severely tested. The astronomers are confident that the relative ease with which they identified this signal suggests that similar sources are waiting to be identified across the galactic plane. Just like GPMJ 1839-10, these other signals might already be lurking within the data we have already collected. Identifying more of these signals will undoubtedly shed light on the process that powers emission beyond the neutron, Star Death Valley. Whatever lies behind the 22-minute signal, we are almost certainly on the verge of learning about an entirely new phenomenon that we have never before witnessed. Isn't that exciting? What do you personally believe could be the source of the 22-minute signal? Let me know in the comments below. Now, so far this video has revisited a lot of content we've explored in the past, but there have recently been some truly mind-boggling discoveries in outer space. In fact, every single week seems to bring a new breathtaking image released by one of our many telescopes on Earth or in orbit, or a major breakthrough that reconfigures how we understand the cosmos. To ensure you stay up to date with these developments, we've launched a weekly newsletter so you never miss the most exciting news, even if the main headlines do. You can sign up for the free Astro newsletter using the link provided below. A new edition is published every Thursday. How much would I weigh on a neutron star? Neutron stars contain the densest known form of matter in the universe, excluding black holes, which defy the laws of physics and are not truly things anymore. A topic better suited for another video. Neutron stars are the highly compressed remains of massive deceased stars, stars large enough to have culminated in a supernova explosion, leaving behind an exceptionally dense core. This core can contain up to 3 times the mass of our Sun, confined within a space only 12 to 30 kilometers across. The material that constitutes a neutron star is termed neutron degenerate matter, a substance composed solely of neutrons. It is packed so densely that a matchbox full of it would weigh 3 billion tons on Earth. This leads to an intriguing point. The concept of weight on Earth is defined by an object pressing down on the planet due to the force of Earth's gravity. Yet, the metric we commonly use to describe something's weight is actually its mass. For example, if I state that I weigh 70 kilograms, that is technically my mass, not my weight, because my weight is the measure of the gravitational force acting upon that mass. On Mars, my mass of 70 kilograms remains the same, but my weight is lighter because the force of gravity is weaker there. On a neutron star, all that mass squeezed into the smallest possible space means that the gravitational force is 2 times 10 to the power of 11 times greater than Earth's gravity, or 200 billion times stronger than on Earth. To offer some perspective, this means that if I were to drop from a height of just 1 meter above the surface of a neutron star, I would impact the ground at a speed of 1,500 kilometers per second. Its gravity is so intense that light can be bent into orbit around it, which means that from certain vantage points, you could theoretically observe the entire neutron star at the very same time. Therefore, although this scenario is far outside the realm of possibility, if I were able to stand on a neutron star, my weight would be 200 billion times greater than it is on Earth. Imagine the immense force I would be exerting on the neutron star's floor. Not that the star would be affected, given its extreme density. What would actually happen to my fragile body is that it would be instantly flattened against the surface, down to the atomic scale, likely being converted into neutron degenerate matter as my atoms are crushed. This powerful gravitational field also makes neutron stars the most perfect spheres in the entire universe, likely possessing an incredibly smooth surface. An unseen antimatter factory 800 light-years away. 800 light-years away, an unseen antimatter factory is constantly churning out high-energy positrons. These tiny particles of antimatter stream through the cosmos and eventually collide with our planet. For much of human history, we were unaware of this strange source's existence. The majority of the positrons bombarding us went completely undetected, as they were absorbed high up in our planet's atmosphere. It wasn't until we began observing from beyond the boundaries of our planet that we noticed them. In 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art particle detector situated approximately 200 meters up aboard the International Space Station, was powered on. What did it find? You guessed it. Positrons. The presence of these subatomic particles was anticipated, but not in the sheer numbers that were being recorded. The volume of positrons being detected was so enormous that the typical sources, such as natural radioactive decay and cosmic rays, could no longer provide an adequate explanation. So, from where were they originating? We have only recently been able to trace the culprit responsible for this cosmic antimatter shower. And it all leads back to another high-energy discovery, a strange gamma-ray haze named Geminga, which was first identified in the 1970s. What exactly is this mysterious source of gamma radiation? And what connection does it have to the unusual abundance of high-energy positrons hitting our planet? I'm Alex McCone, and you're watching Astrum. Join me today as we tune into the enigmatic frequency of Geminga, whose persistent gamma radiation has illuminated the field of astrophysics for decades. High up in our night sky, nested within the Gemini constellation in the northern celestial hemisphere, something peculiar is taking place. In 1972, NASA's Small Astronomy Satellite 2, or SAES-2, identified an unknown source of gamma radiation. However, given the limitations of the technology available at the time, the best it could do was trace the radiation's origin to a wider region of our Milky Way. Consequently, the ultimate source of the radiation remained hidden among the stars for decades. Nonetheless, it was given the name Geminga, as coined in 1976 by Italian physicist Giovanni Bignami, who would dedicate his career to studying it. The name is a play on words, combining Gemini, the region where it is located, and gamma, the type of radiation it emits. Geminga also functions as a pun in Bignami's Milanese dialect, meaning it's not there, a fitting name for a gamma-ray haze of unknown origin. It wasn't until 1983 that Bignami and his team finally achieved a major breakthrough. They successfully identified a faint X-ray signal emanating from Geminga using the Einstein X-ray satellite. This discovery meant that while its exact position was still unknown, they could significantly narrow down their search area, bringing them closer to uncovering Geminga's hiding place. But it still failed to answer the fundamental question: what is it? At that time, astronomers could only offer vague speculation regarding the source's true nature. That changed in 1991, when they had another stroke of luck. Two separate missions identified radiation coming from Geminga, and crucially, these were not constant signals, but pulses. The first of these discoveries was made with a German-built X-ray telescope known as ROSAT, short for Röntgen Satellite, named after the German word for X-rays. ROSAT was the first to identify pulses within the X-ray signal originating from Geminga. Soon after, these pulses were also confirmed in the gamma wavelengths by the Energetic Gamma-Ray Experiment Telescope, or EGRET, a telescope aboard NASA's Compton Gamma-Ray Observatory satellite. Not only did these complementary observations demonstrate that both the X-rays and the gamma rays were coming from Geminga, but for the first time, they unveiled what Geminga truly was. With a period of 0.237 seconds, flashing as it spins around its axis a little more than 4 Hertz, or 4 times per second, Geminga behaved like a pulsar. A pulsar is a type of neutron star that rotates rapidly, emitting focused beams of radiation that sweep across space like a cosmic lighthouse. When observed from across the galaxy, most pulsars appear to flash in radio waves anywhere from a few times a minute to as fast as 700 times per second. And at that point in the early 90s, they were incredibly rare. You see, prior to the discoveries made by ROSAT and EGRET, only 2 other high-energy gamma-ray pulsars had ever been identified: the Crab and Vela pulsars. The Crab and Vela pulsars were distinct from Geminga in a couple of key ways. Firstly, in addition to gamma rays, both of these pulsars also produced radio waves and were therefore detectable using radio telescopes. Consequently, if Geminga was confirmed to be a pulsar, it would be the first discovery of one that was apparently radio silent, only emitting enough radiation to be observed in the gamma and X-ray wavelengths. Secondly, the Crab and Vela pulsars were each surrounded by their respective nebulae, the remnants left over from the supernova explosions that created them. However, Geminga's nebula was conspicuously absent. So, why is Geminga, this powerful source of gamma rays, so skilled at hiding from our radio telescopes? Where is its nebula? Or could it be an entirely different type of object? Well, the answer to the first question is partly because we hadn't been listening correctly, due to both the limitations of the available technology and our incomplete understanding of the radio emissions from such stellar remnants. You see, while radio pulsars can emit radio waves across a wide bandwidth, ranging from as low as 17 megahertz to above 87 gigahertz, covering around half the radio spectrum. Not all of these frequencies propagate efficiently through space. Even though we have known since the 1970s that radio pulsars frequently peak between 100 to 200 megahertz, where they are intrinsically brightest, factors like the interstellar medium, background sky temperature, and effects from the ionosphere dampen lower frequencies as they traverse space. This results in extremely faint signals that are much harder to detect. Because those radio signals were so weak, most radio telescopes had not been searching for them, instead confining their searches to signals between 430 and 1,600 megahertz. This approach would have been fine had Geminga behaved as expected for its kind. Since it did not, it took until 1997 for scientists to grasp what was happening. 3 independent observations from the Pushchino Radio Astronomy Observatory were able to identify extremely weak pulses from Geminga using a highly sensitive transit antenna. The faint radio pulses were centered around 100 megahertz, which fully explains why previous radio searches for Geminga had come up silent. It turns out Geminga wasn't truly hiding. It had been sending us signals all along. We simply weren't listening correctly. That same year, a team led by the late astronomer Janusz Gill theorized that another reason Geminga had appeared radio silent might be its magnetic field. Models indicated that radio waves could be absorbed or refracted within the pulsar's magnetosphere, leaving only weak pulses around 100 megahertz detectable. This mechanism would effectively render it quiet at the higher radio bands that most telescopes typically used. Confirming Geminga was a pulsar, and specifically a gamma-ray pulsar, was a major achievement. In fact, 99% of its total energy output is in the gamma range, making it one of the brightest gamma-ray sources in our entire galaxy. It is, as it turns out, all that remains after a star several times more massive than our Sun exploded approximately 350,000 years ago. But its relative radio silence and its apparent lack of a nebula were not the only unusual features of this pulsar. When Italian astrophysicists, including Bignami, Geminga's namesake, compared a series of observations from the European Southern Observatory's 3.6-meter telescope and New Technology telescope with observations from the Canada-France-Hawaii telescope, they discovered that Geminga was moving. Not only that, it was traveling at an unusually high speed of around 0.2 arcseconds per year. As a reminder, an arcsecond is a tiny unit of angular measurement used when precise measurements beyond a degree are needed. Within each arc degree, there are 60 arc minutes, and within each arc minute, there are 60 arc seconds. These arc seconds are a common unit in astronomy for discussing the movement of objects across the sky from our vantage point on Earth. If you were to draw a circle around the orbit of the Moon around the Earth, there would be 360 degrees around that circular path. So, at any given time of day or night, assuming nothing obstructs your view of the horizon, you can see about 180 degrees of the sky. And from the horizon to the zenith, the top of the sky, is 90 degrees. If you hold out your little finger at arm's length and close one eye, the tip of your little finger covers roughly 1 degree of the sky. Next time you are outside on a clear night, try this and see if your little finger can cover the moon. It should, because the moon takes up only about half of a degree, or about 31 arc minutes, in the night sky. Geminga traveling 0.2 arcseconds across our sky each year may not sound like much, but from our perspective on Earth, a typical star only moves a few thousandths of an arcsecond per year. Yet, despite being 800 light-years from us, Geminga will traverse 30 arc minutes, the equivalent of the Moon's apparent diameter, across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy at nearly 210 kilometers per second, heading toward the boundary between the constellations Gemini and Lynx. At its current rate of motion, Geminga will remain in Gemini for another 500,000 years, but it may require a new name after that. However, this mysterious pulsar gets stranger still. Its tremendous speed helps to produce another feature that scientists were about to discover. As it hurtles through space, Geminga leaves behind two ghostly X-ray tails that streak 3 trillion kilometers across the sky. As I explained earlier, despite the fact that this fast-moving pulsar is nearly radio silent, it is certainly not quiet in the gamma-ray and X-ray wavelengths. In 1999, ESA's X-ray Multi-Mirror Mission, or XMM Newton, was launched to peer deeper into the X-ray universe. 4 years later, a team led by Patrizia Caraveo uncovered these comet-like X-ray trails. Their shape and brightness are partially explained by the shock wave generated by Geminga's motion through space and its rotation as a pulsar. But they also reveal another attribute: Geminga's colossal mass. Measuring only about 20 to 30 kilometers across, Geminga is extraordinarily dense, containing approximately as much mass as 1.5 of our suns. To put that into perspective, if you had a teaspoon of neutron star material, it would weigh about 4 billion tons, as much as 10,000 Empire State Buildings. As this dense, high-mass object races forward through the low-density interstellar medium, just 0.06 to 0.15 atoms per cubic centimeter, it compresses the interstellar medium and its own embedded magnetic field by a factor of 4. Meanwhile, the incessant spinning of the neutron star creates an environment where electrons and their antimatter counterparts, positrons, can be accelerated to extreme energies, powerful enough to emit high-energy gamma rays. While most of these electrons are seen in the gamma radiation escaping from the pulsar, some become trapped and spiral within this enhanced magnetic field. In these computer model images, the tails can be seen streaking along the edges of Geminga's three-dimensional shockwave, much like the wake created by a boat moving through water. Only this boat is more massive than our Sun, and the wake is composed of extremely high-energy X-rays. But the final piece of the Geminga puzzle wasn't discovered until 2005, its nebula. Taking the form of a shell of neutral hydrogen gas with a radius of 0.4 parsecs wide, it turned out to be what we call a pulsar wind nebula. This type of nebula is created from the wind plasma that emanates from a pulsar's magnetic poles. The plasma, made of charged particles that can be accelerated to near light speed, surrounds the pulsar, creating a nebula of high-energy particles that emit strong X-ray emissions. With the confirmation that Geminga did indeed have a nebula, its identity as a pulsar was definitively confirmed. But Chandra went even further. In addition to imaging Geminga, Chandra also observed a second pulsar called B0355+54. By comparing the two, astronomers uncovered another possible explanation for the absence of radio pulses from Geminga. On the surface, these pulsars appear quite similar. They are both about 500,000 years old, and they spin approximately 4 to 5 times per second. However, as you know, Geminga is seen primarily through gamma-ray pulses with no bright radio emissions. By contrast, the other pulsar, which I will refer to as Pulsar B, is not observed in gamma rays and is instead one of the brightest known radio pulsars. How could these two pulsars be so similar, yet present such vastly different characteristics in how we observe them? The answer may be as simple as the orientation of each pulsar relative to our observation point on Earth. Astronomers believe that these images of Geminga and pulsar B have revealed their spin axes and explained why radio and gamma-ray pulses may be present or absent on different pulsars. Like our own magnetic field around Earth, both of these pulsars have magnetic poles close to their spin poles. These poles are the source of the focused beams of pulsing radio emissions. You could model this by skewering a small foam ball right down the middle. The foam ball represents the pulsar, and the radio beams emanating from the poles are symbolized by the wooden skewer protruding from both ends. If you spin the ball around the skewer, the spin axis, you create an equator around the middle. To illustrate the gamma-ray source along the spin equator, called the torus, you could cut a hole in a paper plate and squeeze it over the foam ball. Now you have a disk of gamma rays beaming out from the equator in every direction. With Geminga, the edge of the paper plate is pointing towards us, meaning the gamma rays are heading towards Earth. But for pulsar B, its relative position to us is at a different angle, as if we are looking at the flat surface of the plate. The gamma rays are moving perpendicular to our line of sight, and therefore miss Earth. Let's look again at the two Chandra images of Geminga on the left and pulsar B on the right, along with artist illustrations of what astronomers believe the pulsar wind nebulae look like for each. In the image of pulsar B, the long, trailing blue tails represent the radio jets emanating from its poles, like the skewers coming out of both ends. Only, instead of being straight like a wooden skewer, pulsar B is moving so quickly through space that these jets appear bent backwards, trailing behind as the pulsar moves. Now, look at the image of Geminga here. The long twin tails on either side of the image are the radio jets trailing behind as it, too, rushes through space. But this time, instead of pointing almost directly toward and away from our vantage point on Earth, these jets appear to be coming off to the sides, not aimed at Earth. So, when astronomers observe Geminga, they detect powerful gamma-ray emissions from the spin equator, but the radio jets point to the sides and remain unseen. And when they observe pulsar B, the opposite occurs. The radio jets are pointed almost directly toward our planet, while the gamma-ray source at the equator is missing Earth. Sometimes the simplest explanation is the correct one, and that finally brings us back to the decades-long mystery of the unusual abundance of antimatter bombarding our planet. For more than a decade, a particle detector called the Alpha Magnetic Spectrometer 2, or AMS-2, has been affixed to the International Space Station, collecting data on antimatter, dark matter, and cosmic ray sources. As a reminder, cosmic rays are energetic particles, fragments of atoms, that travel through space at nearly the speed of light. These can be generated by the sun, by supernova explosions, or by other cosmic processes. In 2013, the first results from the AMS-2 experiment were announced. The detector had recorded more than 400,000 positrons, representing the largest sample of cosmic ray positron data ever collected, and increasing the world's total cosmic ray positron data by 100-fold. For years, many astronomers and physicists hoped that this excess antimatter might be the byproduct of a dark matter annihilation event, potentially offering clues about this mysterious substance. After all, dark matter is thought to comprise around 27% of the cosmos, yet we still do not know what it is. Like regular matter, dark matter possesses mass and occupies space, but it does not appear to absorb, reflect, or interact with light, at least not in a way we can detect. Some theorize that dark matter may be composed of as yet unidentified types of particles. Whatever its nature, scientists held high hopes that the overabundance of antimatter detected aboard the ISS might hold keys to dark matter's true nature. Unfortunately, they have been left disappointed. The deeper scientists delve into the data, the clearer it is becoming. The most probable source of these positrons may actually be pulsars. Astrophysicists had long suspected this, but until 2017, concrete proof was lacking. It was the High-Altitude Water Cherenkov Gamma Ray Observatory, HOWC, that finally provided evidence for this hypothesis. A small halo of gamma radiation was identified surrounding Geminga, with trillions of times more energy than is visible to our eyes, ranging from 5 to 40 trillion electron volts. This is the sort of radiation typically produced by positrons. This was the first real observational evidence pointing to a pulsar as a potential source. Pulsars naturally envelop themselves in a haze of both electrons and their positron counterparts as a direct result of the star's intense magnetic fields. This intense magnetic field draws particles from the pulsar's surface and accelerates them to near the speed of light. Scientists theorize that these accelerated positrons and electrons then collide with starlight, boosting the light to higher energies, which then radiates as the gamma-ray halo observed. However, based on the size of the halo the HAWC team observed, Geminga's positrons would rarely have the energy required to reach our planet. Consequently, they initially believed the excess positrons must have a more exotic source. That was until stunning new information was uncovered a few years later, thanks to a team led by astrophysicist Matteo Di Mauro. Using a decade of gamma-ray data from Geminga, acquired from Fermi's Large Area Telescope, which is capable of observing lower energy light than the HAWC Gamma-Ray Observatory, Di Mauro's team was able to subtract out all other gamma-ray sources. This process revealed a spectacular glow emanating from Geminga, a glow far, far bigger than what the scientists had ever seen before. The vast, oblong halo of glowing gamma rays, at an energy of 10 billion electron volts, spanned 20 degrees of the sky, an area similar to that occupied by the Big Dipper constellation. And that's not all. The glow of gamma radiation is even larger at lower energies. If we could perceive it all with the naked eye, Geminga's gamma-ray glow would dominate our sky, covering an area 40 times bigger than the full moon. With this new information, astrophysicists found that the massive size of Geminga's halo meant that this one pulsar alone could be responsible for as much as 20% of the excess positrons detected near Earth. From this, it is a small step to imagine that other pulsars are the most likely source for the remaining abundance of antimatter we have found. This explanation may not have resolved the mystery of dark matter, but it is certainly a magnificent revelation in its own right. It was Jocelyn Bell who discovered the very first pulsar in 1967, back when people initially speculated that those regular signals could be the work of extraterrestrial life. In the nearly 60 years that have passed since, we have identified thousands of pulsars, and our understanding of these neutron stars has grown with everyone. And since Geminga was identified as only the third known gamma-ray pulsar in 1991, we have now spotted over 300 more, thanks to NASA's Fermi mission. But given Geminga's history of defying expectations and pushing the boundaries of science, I like to believe that this particular pulsar has more secrets yet to reveal. The faint hum of spacetime tune into the universe with the right equipment, and you will hear it humming, no matter where you look in the sky. Of course, it's impossible for sound to travel in the vacuum of space. Instead, we are referring to the hum of gravitational waves. You might already be familiar with a similar background signal discovered decades ago. It is called the Cosmic Microwave Background, CMB, and it represents the afterglow of the Big Bang. This glow of microwave light was a groundbreaking discovery. It served as the smoking gun that solidified the Big Bang's position as the leading theory for the origin of our universe. Yet, this light signal had one glaring weakness. Despite being the earliest light from our universe, it was emitted almost 400,000 years after the Big Bang occurred. If we want to peer further back in time, we will need a background signal composed not of light, but of the ripples in the fabric of space-time itself. In 2023, astronomers working for the NANOGrav collaboration announced that by employing a clever technique, they may have detected exactly that. Using exotic stars as a galaxy-sized gravitational wave detector, they measured the faint hum of space-time itself. This background hum of gravitational waves might just be the reverberations from the very moment of our universe's creation. Music. I'm Alex McCone, and you're watching Astrum. Join me today as we learn about the secrets held within these gargantuan gravitational waves and the ingenious new method astronomers have used to detect them. In a previous episode, we discussed the LIGO detector and how it uses lasers to precisely measure the minuscule changes in the length of a tunnel caused by passing gravitational waves. These gravitational waves stretch and compress space-time, causing variations in the time it takes for light to travel from one end of the tunnel to the other. But detectors like LIGO are only sensitive to a specific kind of gravitational wave. Like light waves and sound waves, gravitational waves exist across a spectrum of different frequencies, and LIGO is only capable of listening in on one segment of this spectrum: the high frequencies. These high frequencies occur when massive binary objects are rapidly spiraling toward each other, completing hundreds of rotations per second before colliding in a great bang. But that is also why LIGO cannot detect the much earlier stages of these binaries, when the objects are orbiting each other at a much greater distance. Because these orbits are significantly slower, the gravitational waves they generate are of a lower frequency and energy. So, rather than a great bang, they collectively emit a faint hum, combining into one collective signal. More massive black holes contribute more strongly to this background signal. The loudest contributors would consist of pairs of supermassive black holes, the type typically found at the centers of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are expected to be rare because they only form when something truly spectacular happens: the merger of two galaxies. When galaxies merge, due to the vast amounts of empty interstellar space between stars, they mostly pass through each other. Very few, if any, actual collisions between stars or planets occur. However, the stars gravitationally attract one another and merge into one collective galaxy. Crucially, the nuclei of these galaxies, the supermassive black holes, form binaries that continue orbiting each other long after the galaxy merger appears to be complete. It is these remnants of galaxy mergers that we would hear most distinctly in the ultra-low frequency range, specifically around the nanohertz range. Yet, just as the human ear cannot perceive sounds with ultra-low frequencies, LIGO is deaf to this cosmic cacophony. If we could listen in, we would gain new insights into galaxy mergers and black holes. But that's not all. One of the most thrilling aspects of the gravitational wave background is that it offers a direct window into the very first moments of our universe's existence. Let's quickly recap what we know about the cosmic microwave background. This microwave light is the earliest light we can detect, because for the first 400,000 years, the universe was opaque. To light. What does it mean for the universe to be opaque? Initially, the universe was far too hot for neutral matter to exist. Electrons and protons were unable to bond together and form neutral atoms simply because they possessed too much energy. This state of matter is called plasma, the same stuff that stars are made of, and the universe was filled with it. Light gets trapped in plasma, unable to move through space without constantly colliding with the charged electrons and protons, being continuously absorbed and emitted. But once the universe expanded and cooled down sufficiently for protons and electrons to coalesce into neutral hydrogen and helium atoms, it suddenly became transparent. The light was finally free to travel. This light was then stretched by the expansion of the universe until it was red-shifted into microwave light. This is why the cosmic microwave background represents the earliest light of the universe. But gravitational waves are not composed of light. They are made of space-time itself. Plasma presents no obstacle to them. For gravitational waves, the universe has been transparent from almost the very instant of the Big Bang itself. They can penetrate past this plasma barrier, offering us a glimpse of the absolute first moments of the universe's creation. Because these primordial gravitational waves have been traveling for so long, even if they were originally produced with a high frequency, they would be immensely stretched by the expansion of spacetime. They would be redshifted into ultra-low frequency gravitational waves, the same kind that would originate from black hole binaries. Together, these multiple sources create what is called a stochastic gravitational wave background, existing over a range of low frequencies. How can astronomers possibly retrieve this treasure trove of information about black holes, the Big Bang, and more? Can we construct a better LIGO and detect how the Earth is bobbing up and down in these gargantuan gravitational waves? Well, LIGO operates by sending two beams of light along perpendicular tunnel arms. The beams are reflected by mirrors at the ends of those tunnels and return to the starting point, where they are compared. This setup ensures that if spacetime is distorted along one direction, the information from the other direction can be used to gauge precisely how much it has changed. Unfortunately, if we were to design a new LIGO to detect these specific gravitational waves, we would require tunnel arms far larger than anything we could possibly build on Earth. This requirement stems from the fact that a wave's frequency is inversely proportional to its wavelength. Ultra-low frequency waves possess an ultra-long wavelength and would necessitate us observing changes over a much greater distance to notice the effects of these gravitational waves. For nanohertz waves, where one full fluctuation takes 1 billion seconds, a quick calculation: wavelength equals speed of wave over frequency tells us that the wavelength would be around 10 to the power of 17 meters. For a sense of scale, the distance between the Earth and the Sun, 1 astronomical unit, is 10 to the power of 11 meters. A light year is approximately 10 to the power of 16 meters. The wavelengths we are discussing are tens of light years long. Clearly, we cannot build anything suitable for this task on Earth or even within the solar system. We need to look far beyond our stellar neighborhood. But rather than wait for humanity to transcend the confines of our solar system and become a spacefaring civilization, astronomers at NANOGrav have employed a clever trick. You may recall our recent episode on pulsars and how we discussed that these ultra-dense neutron stars are capable of spinning with remarkable stability. They emit light along their poles, and we can detect the pulses we receive as those immense beams of light sweep around and strike the Earth repeatedly. These pulses arrive with such precise certainty that they are utilized as the clocks of the cosmos, capable of keeping time across vast distances. Therefore, we can use already identified pulsars to provide us with reliable signals from thousands of light years away. The pulsars act like the mirrors at the end of the LIGO arms. But instead of reflecting a signal we sent across, they are generating their own. NANOGrav has cleverly conceived an imaginary interferometer that stretches for thousands of light years. And all we need to use it are the good old radio telescopes that we have been operating for decades. However, our calculations will only be as accurate as our observations. When selecting pulsars to observe, we must ensure they are suitable for the task. The best candidates are carefully handpicked and added to a group called a pulsar timing array. For NANOGrav, they utilized 68 pulsars chosen for the following special properties. They had to be spread all across the sky so we could determine how these massive gravitational waves are influencing spacetime in all directions. They also had to be millisecond pulsars, meaning they complete millions of rotations per second. In our recent pulsar video, we discussed how these fast-spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses. In fact, their stability even rivals that of some atomic clocks. We could not ask for better timekeepers to be scattered across space and time. This regularity means we can take precise measurements of the time their pulses arrive and continue taking these measurements over multiple years to see if any changes are occurring. Naturally, the times of arrival can vary due to all sorts of factors, such as the constantly changing distance between the Earth and the pulsar as both objects move through space. But we can account for this quite easily. However, there are less predictable factors, such as random fluctuations in the interstellar gas the light is traveling through, causing delays that are not caused by the stretching of spacetime. How do we eliminate the random noise in our data from pulsars located thousands of light years away? With statistics. We can isolate the gravitational wave background from the random noise by considering the correlations between pairs of pulsars in the pulsar timing array. Just like LIGO, one tunnel is insufficient. We need 2 pulsars on each end of our imaginary tunnels. If similar fluctuations show up with 2 pulsars, it is highly unlikely that random noise aligned in such a way to make it appear by chance that they are acting in unison. It is far more probable that a common cause underlies both those fluctuations, such as the possibility that the photons from the 2 pulsars are riding the same gravitational wave as it washes past both of them. We can then relate these correlations of pulsar pairs with the angular distance they are separated by in the sky. If there is no gravitational wave background, we expect there to be no correlation, and the graph should show a straight line at 0. However, if the data displays a specific curve called a Hellings and Downs curve, that would strongly indicate that a gravitational wave background is responsible for the variances. That is exactly what NANOGrav has succeeded in doing. On the 28th of June, 2023, based on over 15 years of continuous observations of their 68 pulsars, they announced strong evidence for the gravitational wave background. This is the graph we have been anticipating. This curve is a hallmark of gravitational waves, which stretch along one direction and compress in the perpendicular direction. This is exactly what we are observing with this graph. When pulsars are separated at right angles, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data appear quite large, but the researchers have calculated that the data indicates the existence of a gravitational wave background is statistically significant at the 3 sigma level. This means there is only a 1 in 1,000 chance that this is a false alarm, and that this data was the result of mere chance. In physics, the 5 sigma level is considered the gold standard for a definitive discovery, but 3 sigma is still very strong evidence. As they continue to collect and analyze more data, astronomers will be able to reduce those error bars and eventually announce an official discovery. So, what secrets does this gravitational wave background reveal? While we cannot isolate the sources of the collective noise just yet, we hope that these techniques will eventually allow us to listen in on specific supermassive black hole binaries and determine what the signal can tell us about the creation of the universe. Until then, astronomers will continue to use their galaxy-sized detector to calculate how we are bobbing up and down in the turbulent sea of spacetime. Have you heard about NANOGrav before? What secrets do you think gravitational waves could reveal? Let us know in the comments below. Space's brightest explosions. Every year since 2018, astronomers have detected a mysterious blue flash in the sky. It is one of the brightest phenomena in the universe, an explosion that makes the average supernova look like a faintly lit candle in the distance. Some have been spotted closer to us, and others are billions of light years away. They appear similar enough to one another, but no one knows what they are or what causes them. Through rigorous observation and analysis, astronomers began decoding a pattern and formulating a tentative but plausible theory until, in 2023, they witnessed something that left them completely baffled. These explosions are known as luminous fast blue optical transients, and there is simply nothing else like them in existence. I'm Alex McCone, and you're watching Astrum. Join me today as we dive into the mystery of space's brightest explosions, covering how they were discovered and why they continue to stump scientists again and again. As this is such a recently discovered event, the data we possess on luminous fast blue optical transients, or LFBOTs for short, is minimal. The first LFBOT ever detected was identified just 6 years ago in 2018, and we have only witnessed a handful of them since. Since so little is known about them, achieving a universal definition remains a little tricky. For now, what scientists do agree on are some common characteristics these LFBOTs appear to share. So far, they all display a predominantly blue emission, very high optical luminosity, and are bright in X-rays, ultraviolet light, and radio waves. They are also very fast, as their name suggests. LFBOTs discharge like a cosmic camera flash. They achieve peak brightness and then dim very rapidly, usually within a matter of hours or days. As you may know, a supernova follows a similar pattern of brightening and then dimming, but this dimming process takes weeks or months. This short-lived nature of LFBOTs makes them inherently difficult to spot and study. So, how did we manage to capture such an elusive event? NASA's Atlas HKO telescope in Hawaii is part of an early asteroid impact warning system that scans the entire sky multiple times per night for moving objects. On the 16th of June, 2018, Atlas HKO was performing its routine scan when it captured something very unusual, a flash 100 times brighter than a regular supernova that vanished within days. The scramble was on. Scientists immediately began analyzing the data to understand what they had observed. They pinpointed the explosion as originating from the Hercules constellation, some 180 million light-years away. Officially designated as AT 2018 COW, the event was affectionately nicknamed the Cow after the last 3 letters in its name. Once located, it was quickly classified as a Type 1b supernova. This kind of supernova, also known as a core collapse explosion, is formed when massive stars collapse under their own gravity. But something about this particular explosion didn't quite fit the mold. When examining the Cow's emission spectrum more closely, it didn't look entirely typical for a Type 1b supernova. It had unusually broad emission lines and very weak helium lines. Scientists initially thought it appeared more reminiscent of a Type 1 CBVL supernova, and so it was quickly reclassified. However, the more scientists pored over the data, the more surprised they were by what they found. Whatever this explosion was, it began to look less and less like a supernova, at least not the kind of supernova one would expect. For starters, it appeared out of nowhere. This blast went from inactive to peak luminosity in just a few days. As we mentioned earlier, supernovae usually take a few months to reach their brightest and dim again at a similar pace. Not only that, it was registered to be 10 to 100 times brighter than an ordinary supernova. Also, everything about the way it exploded was wrong. When supernovae explode, they tend to release their energy in a spherical shape. We now know that the shockwaves sent out after a supernova can be aspherical due to the presence of strong magnetic fields, which can distort the shape of the initial blast. However, upon closer inspection, this mystery explosion did not even explode spherically. The researchers themselves dubbed it the most aspherical explosion ever seen. Soon enough, other theories were being proposed. Some suggested the cow could be a monster black hole shedding a passing star. Others hypothesized it was a supernova that gave birth to a black hole or a neutron star. But let's pause for a moment. It is extremely difficult to draw any solid conclusions when you only have one of something. As the saying goes, once is an anomaly, twice is a coincidence, and 3 times is a pattern. What researchers truly needed was a bigger sample size, more instances of this type of explosion, so they could compare observations and deduce any patterns that might arise. Fortunately, it didn't take long for scientists to set their sights on a second similar explosion. A few months later, in September 2018, the cosmic camera flashed again, and again for a third time in 2020. Keeping the tradition of deriving animal nicknames from the last 3 letters of their official names, we had the beginnings of an LFBOT zodiac. The cow was joined by the koala and the camel. And just like that, they had data on 3 separate LFBOT events. They could finally start hunting for patterns. When analyzing the cow, the koala, and the camel, one of the first things that stood out to researchers was the location of these events. Even though they all occurred in different parts of the universe, each blast was registered as coming from inside the spiral arm of a galaxy. At first, this information bolstered the initial theory that LFBOTs were merely a type of core collapse supernova. Let me explain why. The type of star that causes a core collapse supernova is a massive star, one of the biggest types of stars you can find. And as you know, the bigger the star, the shorter its lifespan. This means that these stars do not get the chance to travel very far before they die. It would therefore make sense that their supernovae occur very close to the star cluster where they were born. And what part of the galaxy is renowned for having such clusters? Yes, the spiral arms, the exact location where all 3 LFBOTs were observed. But just as researchers seemed to be making progress, something happened that caught them completely off guard once more. Like the Atlas HKO in Hawaii, the Zwicky Transient Facility is a very wide-angle, ground-based camera that scans the entire northern sky every 2 days. In 2022, it detected another similar explosion, except after the initial blinding flash, this optical transient began behaving rather strangely. Instead of exploding once and fading away in a few days like the other LFBOTs before it, the so-called Tasmanian Devil continued to produce short-duration bursts far longer than expected. What's more, each of these bursts seemed to be just as bright as the original explosion, which was exceptionally strange indeed. The Tasmanian Devil emitted more energy than hundreds of billions of stars like our Sun combined. Researchers were deeply puzzled, yet again. It was unlike anything they had ever witnessed before in astronomy. Now, I know the skeptics among you may be thinking, Alex, This must be due to some kind of technical error, miscalibrated equipment, a fluke in quality control tests, or a simple mathematical mistake. Indeed, the history of science is filled with scientists shouting "Eureka!" at supposed breakthroughs or discoveries, only to be deflated once someone double-checked their workings. But this is not one of those moments. The data was corroborated by 14 other telescopes around the world. They confirmed that the Tasmanian Devil did, in fact, pulsate a minimum of 14 times. The total number of bursts was likely much higher. Equally surprising, these mega-powerful pulses were only minutes apart. To scientists, it looked like a star that kept dying and being revived again and again. If that's what it is, the strange phenomenon could provide brand new insight into the life cycle of stars. So far, stellar life cycles have only been studied as snapshots of different stages, never as a continuous process. In short, even though the multiple bursts of light from the Tasmanian Devil were unexpected, there was still reason to suspect these explosions could be a strange type of supernova, seeing as none of the observations directly violated the core collapse supernova theory. But what came next did. On April 10, 2023, astronomers picked up yet another big blue explosion with all the same characteristics as its LFBOT zodiac relatives, except this one was not even close to where it was supposed to be. Unlike all the other LFBOTs before it, the Finch was not located in the spiral arm of a distant galaxy. 3 billion light-years away from us, and 15,000 light-years from the closest galaxy, it stood solitary in space. It was truly in the middle of nowhere and exploded between two galaxies. This was a major blow to the leading theory. If these explosions really were the result of massive stars' core collapsing, there is no way it would be happening in between galaxies. So it was back to the drawing board for researchers. They came up with two new theories to explain what could have caused the Finch to explode where it did. The first theory suggests that the Finch could be the result of stars being torn apart by an intermediate mass black hole. A black hole that has 100 to 10,000 times more mass than our Sun. The problem is that the existence of these black holes has never been proven. Their smaller and larger relatives, stellar remnants and supermassive black holes, have both been confirmed to actually exist. But this middle child remains purely theoretical. However, should they exist, could they be responsible for this elusive light show? Astronomers have shown in simulations that stars can orbit intermediate mass black holes as many as 5 times before being ejected. With each orbit around the black hole, the star is effectively being ripped apart, losing more and more mass. Finally, the remaining stellar matter would be flung back out into the galaxy at speeds as high as 10% the speed of light. This velocity would be consistent with the speed and brightness observed in LFBOTs, lending weight to this theory. One of the most probable locations researchers would expect to find intermediate mass black holes is in globular star clusters in a galaxy's outer halo. Galaxies possess halos that extend far beyond the main disk and bulge. They are most visible in spiral galaxies like our Milky Way. In our own home galaxy, the outer halo stretches an impressive 1 million light-years from its galactic center. Some scientists think it is possible that the Finch could have been located inside a globular star cluster such as this. If this is the case, and intermediate mass black holes do exist there, it could be plausible that the Finch was caused by these unusually sized black holes ripping up large stars. The second theory researchers put forward suggests that the Finch could have been the result of 2 neutron stars moving toward each other in increasingly tight spirals until they collided. This type of event causes a kilonova, which is known to be one of the biggest stellar blasts in the universe. One telltale sign of a kilonova is the presence of gravitational waves, which come through as a characteristic chirp caused by a rapid increase in frequency as two massive objects spin around each other, eventually colliding and merging. If we could find something like this when analyzing data from the Finch, it would lend strong credibility to the neutron star theory. However, due to unfortunate timing, our chirp detector, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was down for maintenance at the time the Finch occurred. That means we don't know if such gravitational waves were emitted, as we have no data on them. One thing we do know is that no gamma-ray burst was detected, which is something you might expect to see with a kilonova of this size. But remember, this explosion happened 3 billion light-years away. That is a truly immense distance. Perhaps it was simply too far for whatever gamma-ray data there might have been to be detected. All in all, none of this data can conclusively confirm or reject the neutron star theory. It is frustrating to witness such an incredibly rare, new, and powerful phenomenon and not possess the data to conclusively understand what is causing it. I suppose patience is an underrated virtue for an astronomer to have. But they are not sitting idly by either. Scientists are already planning to utilize the optics of the James Webb Space Telescope to carry out a search for any faint globular clusters in the same location as the Finch. This would hopefully clarify if they are on the right track with the intermediate mass black hole theory. In the meantime, other researchers are focused on expanding the sample size. The more LFBOTs we can detect, the more we will learn about them. The 6 we have observed so far have taught us some things, but we have much left to learn. The only way we are going to acquire a larger sample is to continue sweeping the sky with wide-field surveys like the Atlas HKO and the Zwicky Transient Facility. Scientists' hopes are pinned on the Vera C. Rubin Observatory, currently under construction in Chile, a telescope that will scan the entire southern sky every few nights, which I have done a video about here. It is expected to be operational by 2025 and will be capable of capturing 10 times more light than all previous facilities combined. Follow-up observations with Hubble and ground-based telescopes will help analyze more information, which could lead to more breakthroughs. LFBOTs are a very new phenomenon that we still don't understand well. Scientists themselves admit that the discovery of the Finch raises more questions than it answers. The more we learn about these bright blue explosions, the more they continue to surprise us. All there is left to do is what hundreds of generations of astronomers have done for centuries before us. Point our telescopes up to the sky, watch, and wait. Thanks for watching. I truly want to give a huge thank you to our astronauts on Patreon. It is genuinely becoming a thriving community, and I have loved reading all your messages and comments over there. If you would like to join in, you can visit the link in the description to become an astronaut and provide the channel more stability than the algorithm. When you join, you will be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astram content. I will see you next time.